Hi everyone, and welcome to another video of Programming for Data Analytics 2. Today we're going to be exploring linear regression using scikit-learn. I'm going to run you through one of the basic examples on the website, and then in the next video we're going to take that information and then make our own example that I came up with, which will kind of build upon what we do today. So today's example is literally going to be just kind of mimicking what somebody else has done before and what they have as documentation. And then the next one is going to be the one where we actually get to use that knowledge to apply to our own data set that I decided to pick. So I'll talk about it in the next video, so you'll get to see that. Okay, so scikit-learn has a linear regression function that you get to use, and I'll just pop it up right here. And basically what it looks like if you go into scikit-learn here, let me actually Google that. So scikit-learn linear regression. This is basically the documentation you get. So ordinary least square linear regression, and then you get your parameters and your attributes, the functions that you have, which are your fit function, and just so that we can review the basics of what you need to do when you're doing regression is, first of all, well, you need to get your data, right? So you have to get your data, and then you have to basically take that data and decide what you want your features to be, so your X and Y's. So in fact, it might be easier if we go here. So just to make sure that we remember, the machine learning process was, this will apply not just to linear regression too, but to like a lot of the ones we're going to do is, first you got to get the data, clean up that data, I suppose, decide what your features are going to be. And what I'm saying is your data might consist of a massive table with a bunch of columns, but you might only want to look at a specific number of columns that are going to represent your X axis or your X features, and then one column that's going to represent your Y, which is going to be what your output's going to be, right? So based on the features that you pick to do the machine learning on, so you're going to train it with this in hopes of trying to predict this. And so you got to decide what your feature is going to be. You might just feed everything you have, like literally all your columns, but I think you will find that sometimes it's unnecessary, and it actually may prove, it'll slow things down and prove counterintuitive that you don't want to always just give it every single possible feature that you have. Sometimes you want to just reduce it and figure out if any of these features matter. Some features might actually be completely not correlated to the output, and they might just be noise, and they might actually negatively affect the performance of your algorithm. So yeah, figure that out, decide, test, trial and error, remove things as they work and as they don't, and eventually, once you decide on that, what your X and your Y's is going to be. And your Y is typically going to be only one thing. You could be running multiple linear regressions if you have multiple Y's, but they're different. So each one's going to be its own linear regression with one output, and then the input can be just as many as you want, as many features as you want. Okay? So when you do that, you got to go ahead and create that training and testing split. So you're going to take your bunch of X's and your Y's, and maybe like 80%, and you're going to train it with that. And what that one's saying is, I'm going to feed it the X and Y pairs for 80 of my 100 examples per se. And I'm going to keep testing it so that I hopefully can predict this very accurately. And then once I'm ready to go, the leftover 20%, I'm going to go ahead and test it by feeding it the X's. And then whatever Y I get, hopefully is going to be equal to the Y that I expect, right? So this is the correct Y, and then this is the predicted Y. And so hopefully they're equal. And if they're all equal, then I can say that I have 100% accuracy. If I get some that are not equal, then of course that lowers my accuracy, right? And so that's kind of the chain that we're going to go. Is we're going to get the data, clean it up, select our features, create our model using the fit function. We're going to train the model, and then we're going to use the predict function to actually test the model and see if it worked here, or for any additional new stuff that we get once we're happy with the model. And that's pretty much it. That's all we have to do to get this working for pretty much most of the machine learning scikit-learn functions that are available. And so you can kind of see that here in the scikit-learn documentation for linear regression. Again, this is just linear regression, and you can see this kind of how it goes. You got your fit function, which is what happens when you're training. Your predict function, which is like when you want to test something with it, whether it's you're testing your test data set, or you're like really happy with your model and now you're actually going to use it in the real world to predict like new data, and you call predict for that. Score is that so that when you test a model, sometimes it's not enough to just say whether something is accurate to a certain percentage. That doesn't really tell you the full story. What does it mean for a model to be like 90% accurate? Well, 9 out of 10 times they get us right. Okay, but like, what is right and wrong? Like, I'm not trying to get philosophical, but like, supposing you're trying to predict a stock price, and your model has 0% accuracy because not a single time did it predict the right stock amount. Does that mean your model is horrible and should never be used? Okay, sure. You're like, no, I don't like your model. It has 0% accuracy because it never predicted the right stock price. I'm not going to buy it from you. You kick the person out. And then he goes to another business and they buy it from him. And then the business is making tons of money. And you're like, what? But like it had 0% accuracy. What happened? And then you go and look closer and you're like, okay, what was the model doing? Okay, it was predicting the stock price. Sure, it never predicted it correctly, but it was only off by a couple of cents. And you still got the main sense of what the stock was going up or down. And not just that, but like how much it was going up for, within an error range of about a couple of cents. It just never happened to hit it with the exact down to the penny amount. So the accuracy might look like 0% because you're never hitting it correctly. But within a range of numbers, you're actually doing pretty well. And so that's kind of the shortcoming of just thinking about accuracy. So when it comes to trying to evaluate whether a regression model works or not, you want to look beyond something as basic as accuracy to kind of really evaluate it and compare it with other models. And so there's a couple of different ways of doing that. Some of the popular ones are your mean square error. And also your mean absolute value error. Yeah, mean absolute error. Along with things as like the R2 coefficient, or R2 score, actually, I think it's known as. So how do these work? I'm going to primarily focus on these two for now. So the mean square error, and this is called root mean square error because once you get the mean square error, you take the square root of that, but it's kind of, most people know it as the same thing, is the idea of comparing what the model predicts, which I'm going to call the y-predict. So what we get from a model, compare that to what the correct answer is. So I'll call that like the y expected or something, or y correct. Or another popular term for the correct something is the ground truth of that. Okay, so when you hear the word ground truth, like what is the ground truth of this document? It's what the correct version is versus what you're predicting. And so if I go down here, look at the formulas, so I can remember them. I mean, they're very basic, but yeah, sometimes I get them flipped which one goes before the other one. Although it doesn't really matter because things are squared, but still. So let's look at the mean square error first. So the formula for that one is going to be yi minus lowercase yi squared, and that's why I don't think it really matters much because you're squared anyways. But still, let's copy it as is. the average of that. And then this is mean square error, and if you're doing the square root, then you just the square root, okay, of that. And then for the absolute value, it's going to be also, sometimes they put a little y hat there, okay. And then for the absolute value one, it's going to be the same thing, but instead of doing the square, you do absolute value of that, and that's it. So it's going to be 1 over n, the sum from I to n of the absolute value of these two things. Yep, okay. So what does this mean? What you're doing is you're taking what you expect, and then you're subtracting from that what you got. And that could be a bigger number than 0 or less number than 0, right? So let's think about for a second like the stock, right? Suppose you're looking at GME stock and it's $200, okay? That's what your model predicts. But the real reality of that day is that your model, that it was $198.95, okay? So what you want to do is you want to take the number that is supposed to be correct, and of course this is when you're evaluating, right? Because I mean, you need to know what the right answer is to figure out if something is right or wrong. So this metrics is only useful when you're doing it against your test data set. It's not going to be useful in the real world because you don't know what the answer is, but you can of course do a prediction, and then when you finally get the real answer result, like when the market closes, then you can go ahead and evaluate it again. But yeah, so this is when you're doing with your test data set. So you take the real value versus the predicted value, you subtract them, and in this case you get a negative number of 105, okay? What does this mean right now? This means, and if you take the absolute value of that, you can see that it doesn't matter if this is a positive or negative number. So if you predicted instead something of the line of 197.90, right? The difference between that and the real one would have given you a positive 105, right? So in both of these cases, whether it's absolute value or square root, or sorry, squared, which is what you're doing in either one of these, it doesn't matter whether the number is positive or negative. Which makes sense because, like, you shouldn't punish your algorithm for over guessing or under guessing. It's not like when they ask you a game like, yo, guess a number, and if you go over, or sorry, if you go over the number you lose, but if you go under you win. That's flawed, right? Because like if the number is 100 and you guess 101 and somebody guesses 90, just because you went over by 1, like now you're still more accurate than the one with 90, right? Unless it's a special scenario where like going over is really bad or something, like maybe like drug dosage. You don't want to OD someone, but to underdose them, it's still safe, I guess. Cool. So that's why most of the time we don't care whether it's over or under. We just care the distance from the point that is correct. And so in this case, if our algorithm predicts 200 or 197.90, in both of these cases, the difference is $1.05, positive or negative. So in the case of mean absolute error, what I'm doing is I'm simply just using the absolute value of this, which gets us to 105. And then I'm going to do this again for all of my test points. If you're only doing it with one test point, then you only have one. And so you say, well, my absolute error is going to be of 105, because that's literally the only point. But if you, let's say you had 10 of these errors, one of them is 105, the other one you're off by 95 cents. Maybe like a couple of them you're off by 10 cents only. Maybe there's an outlier that you're off by like $2 and so on. Ultimately, what you do is you take the average of these, right? So you add them all up together and then you take the average. But the reason why you do the absolute value first is because you want to make sure that if you have an algorithm that is constantly giving you plus numbers and negative numbers in the same amount, when you take the average of that, you might actually get a 0% error. because the positives cancel out. So like, let's say that you have only two cases here. One where you guess over $1 and one where you guess under $1. If you go ahead and add this together and then the average of that, you're going to get 0, right? Because 1 plus -1 is just 0 divided by 2, because you have two test points here. It's 0 divided by 2 is just going to be 0, right? So you would say, oh, I have no error. But it's not true. You technically do have error. In fact, all of your points have errors, and then they're small. It's just a difference of 1. Well, that's relative, depending on, if this is supposed to give you like in pennies and dollars is really bad or something, or versus like microns versus like meters, that's more bad, I guess. But yeah, the point is that you do have an error, and you want to make sure that that's sort of conveyed in your error calculations. And so having these positive or negatives makes them cancel each other out, which is not good. So by doing absolute value instead, if you have these 2 points, then you would get that 1 plus 1 is 2 divided by 2 because of the average of two numbers. Then you get a 1, which is more accurate to what your error is, because yes, you are in fact off by 1 in both of these cases, right? So that's why you do the absolute value for the mean absolute value error. You just take the absolute value of all of your errors and sum them all together and do the average. In this case, what would that be? Well, if we have something like this, probably the average is going to be somewhere around 1, about 1, right? I mean, these two give you 1. This one goes really low, but this one goes really high. So yeah, about 1. And that's done. That's your mean absolute error. Now, mean absolute error is pretty good in that, because it's a number that is easy to understand and to really know that, okay, that's what this error means. On the root mean square side, instead of doing absolute value, another trick that you can do to avoid this plus and minus issue is to square the number, because the number times itself is basically going to cancel out any negative numbers, right? So in this case, if we get a 1, 1 squared is 1. If we get -1, -1 squared is also 1, right? So you get rid of the negative numbers that way, which is another alternative to being able to not have issues with the pluses and minuses. And then again, you just take the average of all of these, and that's your mean square error. But it's still squared at this point. So then you got to take the square root of that to kind of go back to the original number. However, that's a lot harder to interpret, because you square things and then you take the root of them after you do the addition together. There is a good thing to this though. And that is that outliers are going to be more noticeable in your root mean square error versus your absolute error. Meaning that when you're doing, when you're trying to see if a model fits well, particularly when it comes to outliers, you want to look at the root mean square error, because outliers are really going to punish your model's accuracy per se. Which is a good thing if that's what you're going after. If you don't really care about outliers and you just kind of want to go with the main chunk of your data, then you can do mean absolute error, which is easier to understand for someone that's just looking at the error number, at the number itself, but also it's less sensitive to outliers, meaning that it's not going to punish your accuracy, even if there's a couple of outliers. Now, what I mean by outliers, just to make sure that we all remember, if we have a bunch of dots that we're trying to predict the line for, that's typically going to be your line, right? And in most cases, the error is going to represent something like this minus what this is here, or this minus this, this minus this, this minus this, right? So this is your errors. This is error, this error, this error. You're going to add all those together. Obviously, you're going to absolute value these numbers so they're all positive, or you're going to square them. But here's the thing. If you have 1 point that's like an outlier, so maybe you have 1 over here, just 1 spot. This is a big error, right? And because you're doing the square operation of this number, because I don't know, this is let's say this is 20, and then here's 3, right? So that number is going to be 17 squared. And you're going to be adding that to all of the smaller errors, which all are like maybe like one of them like 1.5 or something. The biggest one there maybe that you have, which is not, but let's say it will be 2 squared, right? So all these little tiny numbers that are like less than 1, you know, we can just consider 1 for now. When you do this addition, like this is really going to punish it because it's really going to be off by that. So when you finish adding all of these things, you get, let's say you get about 23. Okay, well, actually, this was 19 and 4. No, that's 23 anyway. Take the square root of that, and let's just say it was 25, so it makes my life easy. So the square root is about 5, so under 5, but yeah, this is 5. That's your error. That's your root mean square error, okay? That's punishing. That's very punishing. Actually, whoa, no, actually, wait a second. Hold on. This is actually 4 plus 17 squared. So 17 squared is going to be 289 actually. There we go. So I was a little bit off there. So this is going to be 294. Now take the square root of 294, and it's going to be somewhere like a little bit over 17 basically, right? So we'll just say 17 again. So you can see that this all stuff becomes significant because of how big this number is, right? So your root mean square error for this is going to be basically 17. So you're really, really punished by the outlier. You could see that if the outlier wasn't there, your root mean square error would have been in the order of like 1 or 2. But now it's 17. Now, if we go and look at the mean absolute value of this, you know, let's say we got the same numbers. In this case, we're not squaring them, and so you end up with what I had before, which is 23. Okay, so 23, take the average of that. Oh wait, like, did I not do the average on that one? I squared them all together, added them, but I forgot to do the average. Sorry for that. So actually it's 294 divided by 4. Right? Yeah, 294 divided by 4. Yeah, because you gotta take the average before you do the square root part. Yeah, okay. So that's 73. So then the square root of 73, what's that going to be? Well, 9 times 9 is 81, so it's 8.5 something. So actually, the root mean square error here is 8.5. Okay? Because I forgot to take the average of this. So sorry for that. So that's that. Over here, when I take the average of that, so 23 divided by 4, .75. I should have done that in my head, but oh well. That is going to be your mean absolute error. You can see that this is a smaller number than this. This is much higher because of the outlier, whereas here it's not as high. Now, of course, let's do this version without an outlier. So let's just say that there are only the three points here. In this case, this would be 4 divided by 3, so we're looking at 1.33. And then take the square root of that, which is going to be 1 point something, like 1. Over here, it's just going to be 1, right? Because 4 divided by 4 is 1. So it's going to be slightly bigger than this one. But they're almost the same. Almost the same. Whereas here, you can see how that outlier really made the root mean square error kind of go up versus that. So I really wanted to make sure that you understand this because, yes, the computer does everything for you, but you need to know when something is working or not, when your model is actually predicting well. And it's not enough to just look at accuracy, because with regression, unlike classification that we'll look at later on, with regression, you're trying to predict a line. You know, you're trying to predict something on an ever-growing scale. So you don't have to hit the exact number every single time to succeed in this. There is a certain degree of error that we're willing to accept and still consider something to be very successful. However, because we have to play that game, we need to be able to quantifiably measure whether our model is better than somebody else's model. And that's where these two numbers come in and other things like R2 score. Because they give us a quantifiable number, then I can say, well, if my mean square error is 5 and your model is mean square error is 10, then obviously my model is better, particularly because it doesn't have as many issues with any outliers, because otherwise that number would be pretty high. And also it's good to know that root mean square error versus mean absolute error, what the differences are, so you understand that when you get a situation like this where the root mean square error is really high and your mean absolute error is not really high, then you're like, that's probably because there's some outlier issues, which you might be willing to accept, unless of course you don't want to accept that. That also brings up one more point that I want to talk about, that is overfitting. Beware of overfitting your models to the point that you don't have an error. Your error is really low. In fact, you have a 0% error. But does that mean your model generalizes well or not? If you have some extra data to test, like in the validation set, then you can definitely test it and confirm that issue, if that is an issue. Or if it's not, then you're good. I mean, great job. But more than likely, with machine learning, it's really hard to get 100% on things. In fact, I'm very suspicious whenever I see something that is exceeding close to 100%. Because the only times that you really see it is when you overfit. Now, again, what does it mean to overfit? Okay. Actually, yeah, I had a little picture for that. Let me show you this picture from scikit-learn's website, actually. There's an article, Underfitting versus Overfitting, and it shows you an example of a line, a regression that is okay versus one that's bad versus one that's overfitted. Or underfitted, I guess, versus overfitted. So underfitting means that your algorithm is lazy and it could be better, it could predict better, but you didn't let it run long enough, or it just couldn't find a better solution because of whatever. Overfitting is when you just you tweak it so much to get it so accurate that it's only going to work for your data set and not generalize well. By generalizing well, I mean it's not going to be able to work with other new points that come in. So what does that look like? So the blue dots here represent the actual data. And then the orange is this magical function that is actually the one that you want to get. So that's kind of like your ideal. It might not, I mean, here they call it the true function, but I would not say that's 100% because it's not really touching every single point, but it's kind of like what you want to get. So with a really lazy model, or actually in the case of linear regression, where you're doing actually a line of linear regression, you can see that you really can't fit this too well. But you can do a line like this, and yeah, it kind of works. I mean, you got some errors here, and errors here, right? Root mean square error would really punish you for like this point here, and maybe like this point here and this point here. Whereas mean absolute error would just in general show you some weaknesses because it's far, but yeah, you get that, right? So that's kind of where we're at right now, actually, just trying to do this line. That's what we're doing today. But, if you increase the degree of a polynomial, so like we know that a line is made up of y equals mx plus b or ax plus b, and so actually good moment to review that. So remember, y equals mx plus b, or also seen as y equals ax plus b, where this is the slope of the line, and then this is your y-intercept, right? And what is the y-intercept again? That's basically when you start a graph. Let's do that here actually. This is a very steep slope, very flat slope, right? But you're always starting at point 0. But sometimes you need to offset things because there's a bias. That's why B sometimes isn't referred to as bias. So, you could have a steep line, but you might want to start it here so that it fits the data better. Or you could start it, I suppose, here. What does that mean? That you have like a negative intercept, right? So it's not just about steepness, but also trying to fit it in the right spot by having your bias, okay? So in this case, we call this like 1 degree because we only have one value that computes x. If we have a polynomial function, then we can have as many degrees as we want. And this is a nice little trick to be able to fit data better and to be able to do something with linear regression that's not just a line. So you use a polynomial. We know that, like, for example, when you go to like second degree, you can make a parabola, right? Like x squared makes a u like that. And so that sort of concept is how polynomials work. And so with a degree of 4, you can actually match this curve pretty well. And it generalizes pretty nicely. Even if it kept going, it would actually work out really well. This is probably what you're trying to get. You can see the mean square error here is going to be, and I'll read it out loud. It says 4.08 e to the negative 1 exponent. So it's technically, I guess, 0.4 plus or minus degree of confidence here. Over here now, it's 0.04. So it's a much, much smaller mean square error. So that's pretty good. Pretty good. However, what if you go a little too far? By increasing the polynomials, you can actually go all the way to the number of points you even have, and then actually fit the data perfectly for any data that you get. If you go enough high degrees of the polynomial, you can make it fit exactly. However, it's going to look like a sine wave, essentially. And that's what's happening here. Here, you can see this like goes way down, but it definitely hits all these points pretty straight. In fact, it pretty much hits every single point by just going hardcore with like the degree of 15. So that means this is like y equals ax plus bx plus cx plus dx and so on, like massive stuff. All the way at the end plus some bias, and then gets you this. And in theory, on paper, your accuracy is going to be amazing. In fact, you actually might get like every single dot hitting it. If you have n amount of points and you go to that n amount of degrees, then you'll hit every single point guaranteed. But it's just going to look crazy. You can see how this is really bad. It's going way off the reservation there, essentially, to be able to curve quick enough to hit those 2 points, right? So this is what you want, this is what you don't want, this is not what you want either. You want the middle one, right? So you have to find that balance where not to overfit. So beware of trying to make things so accurate with your test data set that you just overfit it. And graphs are good to see this, graphs are good, but ultimately the validation is what really helps to have that extra testing group. So, okay. This is the example we're going to do. It's an example from the scikit-learn website, and we're just going to pretty much, I'll walk you through the example. And what we're trying to do is we're trying to predict in the two-dimensional, as you see here, we have all these points. We want to make this line. That's what we want to do, because that's the line that we're trying to predict so that we can extend this to the future. Now, I have a really cool graph I found to show you kind of how the prediction happens. So at start, we start with this flat line, because we got to start our algorithm with a initial value. And so we just feed it a 0 or a 1, whatever you started with. And you can see how it slowly works its way to the right spot. That's basically your model iterating through the data repeatedly. Every single time you decrease that mean square error or mean absolute error until you're satisfied with it, and then you stop. Now that's the other thing. In this case, you can see that like iteration 0 through like maybe like 8, it's still moving pretty significantly. But after that, between 8 and 16, it's just slightly adjusting itself. Beware of that. Your model is going to keep running in circles nonstop, and it has to know when to stop. And one of the ways to make it stop is that you are satisfied with the mean square error being like beneath a certain degree. That you're like, okay, I can accept a tolerance of like 0.1 or something. It might take a really long time to reach that. So another way to look at it is, okay, if your mean square error between iterations changes by very little, then you can say that you're done. And you put that as a threshold, what little represents in your scenario. Now, what I mean by iterations, every time that the model gets updated, it updates the slopes per se, it's reading every single point in the graph against its predicted slope. It's checking the error of that. And if it's a little too low, then it maybe increases the slope. A little too high, decreases the slope, recomputes everything again, and so on. Same thing with the bias. And so every time it's doing that computation for all the points, it's going to do one update. We call those iterations or epochs. Each of those takes time, particularly if you have thousands of points to go through and do that simple calculation is not so simple at the end of the day. So you have to find a compromise when you think it's good enough, it's not overfitted, and it's not going to take 10 years to finish. Okay? So just a nice little graph that I found for that. But yeah, okay, so we're going to go ahead and do this example. And first, let's talk about the data set. So the data set is a data set that's built into scikit-learn, so you don't need to download or install anything. And it's known as the diabetes data set. The data set is also discussed in this book. This one, Python Data Analytics, which I've shown before. If you want to check out that, you can. But if not, like I said, it's just a data set that's built in. So the book says this database was first used in 2004. The Annals of Statistics by Efron, Hastie, Johnson, and Tibshirani, and has become effective to study various predictive models on their effectiveness. And then it talks about how to upload it, which I'll show you. This dataset contains physiological data collected on 442 patients and as corresponding target and indicator of the disease progression after a year, so of diabetes. Physiological data occupy the first 10 columns with values that indicate the respective data. So it's like age, sex, body mass index, BMI, blood pressure, and then you got these 6 other sort of values, which they're called serum measurements, S1 through S6. These measurements are obtained by calling a data attribute. But going to check the values of the data set, you will find the values are very different from what you would have expected. And they basically range from what is essentially +1 to -1. Okay? But they're all very close to 0. And so basically we don't really need to know much about that for now, but the reason why those numbers look like that and they don't is because a lot of the times not all the data that we're trying to use to predict something is nice. And by nice I'm saying it's like a nice contained sort of range of numbers. And so that can affect our computations, particularly if you're dealing with numbers that are like massive for one feature and then really tiny for another feature. And so what you want to do to sort of avoid that sort of as a thing that messes up your formula, because ultimately what's going to end up happening is each feature is going to multiply times x, right? So your x is like your feature of data. Oh, sorry, I might have said that wrong. So your x is your feature, and it's going to be multiplying times some number, some coefficient that you're going to be calculating. That's going to be your slope, right? And so if one of the numbers is really, really big and another number is really, really small, the really big number is going to have a really, really small slope to sort of counteract the really small number having a bigger slope to sort of like, so they don't cancel each other out. And then it'll work for the most part, but you'll find that it's not as accurate as if both numbers were within the same number scale, because then they would really be able to that wouldn't be a problem that the algorithm is trying to compensate for, and it can just focus only on trying to predict what is a good slope for this. The way to approach that issue is to do what's known as normalization or standardization. I think that's how you spell that, standardization. Basically, standard deviation, that's kind of where standardization comes from. And normalization is a form of a standardization, and that is basically to take numbers and put them within the range of either 0 to 1 or 1 to -1, depending on what you're doing. And standardization is taking the standard deviation of the numbers, I believe. It's been a while since I've done standardization. Let me double check that. You know, it's sad because that was in my dissertation, but it's been a while. Standardization is a process of putting different variables on the same scale. To standardize variables, you calculate the mean and standard deviation for a variable, and then for each observed value of the variable, you subtract the mean and divide by the standard deviation. So there you go. That's the computation you do. But typically, at least in my practice, I prefer normalization because it tends to work better for machine learning than standardization, or also known as C-scores, by the way. So that's just my advice. But we'll get there eventually. I'm sure. I think in the example that I'm doing next class, I don't do any sort of normalization, but I can probably try to do that later on and see if it affects the error and improves it. So I'll probably give that a go. But I'm more. I think I like doing it more for classification problems than regression problems. But we can try it out later on. Okay. But anyways, so already the data set is standardized for you, the diabetes one. Okay. So that's kind of what we're doing. We are going to try to look at that normalized data. And by the way, the big thing with normalization is you don't actually lose what it represents, and it's reversible for the most part, at least. So that's a good thing, okay? So what we're going to do now is we're just going to try and run through the example. Again, this is not something I came up with. This is from the documentation. My examples that I came up with, we'll be doing on the next video. But I thought I'd start out with this one. It's like baby steps. It's the first time we're using this library. So I want to make sure, and I want to make sure this is one of the libraries that you like religiously use because it's really good. So the first thing I'm going to do with this is I'm going to go ahead and import the scikit-learn library. Now, the scikit-learn library actually, hold on a second. Here we go. I installed it on this VM because I didn't have it installed. So this is what it looks like. Pip to install -u scikit-learn. You can see it took seconds to install, but your mileage may vary depending on your speed of internet and your computer. But it's pretty easy. Just like other libraries would install, just run the command and wait a couple of seconds and you're good to go. Okay, so the way to import that library is you can either import the entire library, or better yet, you can just import what you're going to be using. So for example, oh, by the way, it's sklearn, so don't type in from scikit-learn. Let's say you want to import a data set, because we're going to use a data set that's built in, the diabetes one. So you can say import data sets. You can also import multiple things in one line. So I'm going to import linear models because I'm going to use linear regression. But if you're using another model, then you would import that. Also, I'm going to want to import all those metrics I was talking about so that I can check my quote-unquote accuracy. So I'm going to go ahead and import, and this is a cool thing. You don't need to do that math. Like that little formula I told you, don't need to worry about it because it's already in here. You just have to call it. It's a function. See, look, you got mean absolute error. You got mean square error. yeah, you got them all. So for now, we're just going to do mean square error. And then, actually, no, let's get mean absolute error in there as well. And then maybe R2 score. I don't like that being a very long line. I think I can put that on the next line without just yelling at me. Nah, it will yell at me. Okay. From scikit-learn metrics. I could just import the entire thing. By the way, I could just like literally say import scikit-learn metrics as metrics or something, and not have to import every single function individually. But I thought I'd do it this way because in my example, the next time I actually do it what I just said. So yeah. Also, I'm going to import NumPy just for one line of code that's using this, and then Matplotlib because we are going to get to see some pretty graphs and see if this worked or not. And so are we in the next one too, by the way. I'm pretty excited about those. Well, the graphs for the example that I'll do next time look kind of weird because it's like 4-dimensional, and it's kind of hard to make a 4-dimensional graph. So I made it into a 3D graph, but it doesn't look as cool. But you'll get to see it, and you can judge me then. Anyways, that's what we need to import. So the first thing is, let's go ahead and load the diabetes dataset. And to do that, we need to make a couple of variables where we're going to store our training and our test data. And so again, we want to make it into our features are going to go into the X ones, and the output is on the Y. So I'm going to make two variables, call them diabetes X and diabetes Y. And what I'm going to do with that is I'm going to call this function called load diabetes. And I'm going to turn this on. Don't worry too much about this. This is like a pandas thing. Or NumPy thing, I suppose. Well, no, it's a pandas thing because I believe the diabetes dataset is held as a data frame within scikit-learn. But don't worry too much about that. All you need to know is this dataset is built in basically so people can learn scikit-learn. They also have the iris dataset, which we probably use with classification. Very traditional thing to use, I think, for classification. So they load these data sets in for you to play with. Obviously, when you're going to use this in the real world, you're going to use your own data, right? But it's always nice to have these built in for just to play. And I mean, in theory, if you tweak the algorithm to the point that you make something better than state of the art, then this is like the OG data set to use because like everybody refers to it. So it's nice that they have them here. But yeah, so this is basically how you load them in. I am going to just reduce this because the diabetes data set I said has a bunch of features like all those blood serums and age and gender and whatnot. So I'm just going to take one of the features because I want this to be a 2D graph, and I mean it's an X and a Y. X is one feature and Y is our output, right? If we had two input features, then it would be like XYZ. We're X1 and X2 and Y, right? So that would be like a 3D graph, right? And then if we have more than two features, then it becomes like a multi-dimensional graph, which is actually with the other example that I did where I had three. So case in point. Okay, so we're just gonna make it simple for this one. And just take one feature, basically. Okay, the next thing we're going to do is we want to do the splitting of the testing and training. Now, because I am following this example, all they're going to be doing is literally slicing the array, just hard slicing it at a specific spot. I don't think that's the best way to do it. The best way to typically do your slicing is random, which means you randomly cut into the data so that you just take 20% of it from all over the place. If you just take the last 20 of the first 20, that doesn't work very well in all data sets, particularly in the one I'm going to show you next time. And so it's not a good practice. Again, it's one way to fake your math being better than it is, or actually make it worse. So there's a function within scikit-learn that allows you to randomly split it based on a percentage that you give it as a parameter. Super awesome. But I'll show it to you next time. Again, we're just following the baby example for now. So we're just going to slice it, okay? So for that, we're split into training and testing sets. So again, this is not what I would normally do myself, but it's okay for this kind of example, because these are already like, these are patients in a list, and there's no real order to them in that list. They're already random, so it's okay to just take the last 20%, because it's already like a random list. Whereas in the data set I'm using on the next class, it's not random, it's a time series. And so particularly with things like time series, it would be unfair to just take the last 20%, because that could just be completely different because of some world event. You know, it's like, imagine if you're looking at the time series of like people dying from things, and then you try to predict like the previous 90 years to the last 10 years, and your algorithm keeps getting really bad accuracy. Well, yeah, because there's literally a pandemic going on in the last 10 years that did not happen. Well, I mean, 100 years ago, you probably had like the influenza pandemic and a couple of other epidemics and whatnot. But like, it's clearly going to mess things up. Whereas if you randomly take pieces out of the data, then you will have some of the COVID data on the training and on the test, but you also have other normal years. So it'll probably be trained better, and it'll, in general, perform better. And it'll be more fair when you're testing it, because you get it from the entire time scale of the 100 years, and not just all the last 20 or 10. So hopefully that makes a good argument. But if not, please contact me and I can clarify. So again, we're just going to take a given piece of the data set for training and testing versus randomly getting stuff, okay? Now we gotta do the same thing for the y's, which are the predicted values. So I'm gonna copy and paste. We're gonna call those the target. Sorry, my dog's behind me, is pushing me. And then it's just gonna be the same thing, just with y's instead of x's. Now you notice that I use a lowercase y. It's traditional to use that. For features you use an uppercase, and for output you use y. So yeah. Okay, so anyways, now that we did our nice and split thing, the next thing we do, we don't need to do any cleanup, because again the data set is pre-cleaned up for us. So we will do some cleanup in the next example, next class. So you'll get to see that whole. But again, we're keeping the example short and simple, so that we can then go harder afterwards. You know, baby steps. Okay, so now we gotta create the linear regression model. And the first thing you need to do is you need to basically create an object and store the model in there, like the default model. So any parameters you wanted to put, this will be the time you would do it. But we're gonna keep things simple and just leave everything by default. You can see all the parameters here if you want it to, and those parameters match the link that I showed earlier. Okay, you can see all good stuff. You got some nice examples in here. So lots and lots to go and read. Okay, next we're going to go ahead and train the model. So this is actually where the magic is going to happen. Machine learning is not something you do overnight. Some things take a long time to train, particularly when you're working with a large data set and a fancy model. Like it could take seconds for something like this small, but it could also take days. So just be aware of that, okay? When you're doing your own examples, don't go too big in the beginning, because you might just be stuck there training it for hours, and then you finish it and you're like, can I tweak this variable? Let's try that. Okay, I guess I'll come back tomorrow and see what happens. So that's another argument for why you should know a little bit more of the theory behind the math, like the math behind the models, because while you can always just go in and tweak the parameters and just basically play around with it and hope for the best, when you're dealing with something that takes a long time to train, you want to work smart and efficiently, and so you want to know that the parameter you're tweaking is actually going to have a positive effect because you know the math behind it is sound, versus like, yo, let me just try like changing one of these parameters from like SPMs. Let me just try to change this kernel from like 1 to 2 and see if maybe that works better, when you don't have no clue what the kernel is or what it's good for. So, you know, read the documentation, inform yourselves so that you can do better. And yes, we will have kernels when we get there. So you get to, but we won't really talk much about the different kernels. We'll just say what they are, but you would want to go and read like the Wikipedia on kernels and learn them and see like, hey, RBF is pretty good for most cases, but there's also these other kernels which may have a special case where they actually are better, and so on. Okay, so anyways, for now we are going to make our model fit, which is training, and we're going to pass it our features and our predicted, well, our expected values. So this is what we want to get. So this is the correct answer given for this input. So we're gonna, of course, we're telling it like, yo, this is the input and this is what you should get. So make sure you learn that. So learn like, when you get this, we get this back. When you get this, we get this back. Okay? It's kind of what you're trying to do. You're trying to teach it. Okay? So there's a machine learning, right? I was like, ooh, it's working. Eventually, it's like, okay, I'm good to go. You're like, all right, time to test you. Let's go ahead and make predictions using the test data set. So now what we're going to do is we're going to make a new variable called predict that's going to store the predictions, and we're going to call the predict function for that on the same object that we have here. So this object is our actual model. So we're calling it to predict, and then we'll feed it whatever we want to predict. This could be a single value that we want to test, or it could be, in this case, the entire list of values that is our test data set. So we're feeding it the X test. Again, I want to make sure I don't lose you on this. What your model is giving you back is y equals mx plus b. Okay? Let's just say that let's give it some real numbers so you can see it. It's like y equals 5x plus 1. Okay? Your x is your input. This y is your output. You know, if basically it figure out that these numbers, this is what it learned from after you train it. That 5 and that 1 is what it literally learned and said, like, that's the best numbers that I can put there so that the y is correct most of the time. What you're doing when you're predicting is you're feeding it a new number for the x, and you're going to compare that with what you should get here, and you're going to do the evaluation of whether it succeeds or not after that. But right now you're just going to feed it a new number and then store the output so that you can see if that's a good thing or a bad thing. Okay, so that's what predict is doing. It's doing a prediction. Okay, so now that we have our answers to this, so whatever the model predicted, we want to compare these with what the correct answers are, because we have those, because it's in the test data set. And of course, how do we compare if they're good or bad? Again, we just don't look at accuracy. That's where we have our coefficients, our mean square error, our mean absolute error, all those great things. We can play with them. First thing we can do is we can, and of course I haven't run anything because you can't really see anything right now, but we're finally going to call some print so we can see it. We're going to call regression coefficient. That's going to print some cool things. So let's just run it right now. Make sure it runs. You can see it took a little bit to run. All right, so at least it ran. So let's go ahead and print out the mean square error first. Okay, so I'm going to go ahead and say mean square error. And I'm going to call the mean square error function. And what you need to feed it is your expected answer versus your predicted answer. So feed it first the expected and then the predicted. Although, actually, I don't think it would matter. Yeah, I think you'd be okay either way. Because again, absolute value. If it was square error, the square root, it will get rid of it. So yeah, actually, I think it doesn't matter. But we can test it. We can test it in a second. Okay. I put it in the next line so it looks nicer. Let's run that. All right. Let's compare that by flipping them around. Yep, there we go. Exact same number. Again, it's doing something like predicted value minus expected value, and then absolute value of that. Or actually, in this case, mean square error is squaring that number. So the only difference between flipping them, the subtraction is, in one case you get a positive number, the other one you get a negative number. Both of them basically become positive once you square the number. So that's why it doesn't matter. It's kind of good that we see that happen. Now, mean square error it's not ideal because I told you the reasons why. First thing we want to do for this is let's figure out what the root of this is, like the root mean square error. So let's do square root of this. I didn't save it anywhere. Dang it. So maybe let's take this number and save it here. We got MSE equals this. And then we can say root mean square error, and then do square root of this. Square root not defined. From numpy import square root. Okay, so this is our root mean square error, 50.48. Now, is that good or bad? Let's actually run it again. I want to show you something. Is it giving me the same answer each time? Yeah, it is. Oh, okay, so it's converging on the same spot. I was going to say, sometimes the seed for this is random and might converge differently, but yeah. Okay, so I mean, we have to see what the numbers really mean. So like, it's not, obviously if I knew this data set better, I could tell you whether this is a good number or a bad number. Next time when we know that we use what I understand, I can tell you more about it. But one thing that we could definitely do to better understand it is we could graph it and we could visually see if this is actually a good prediction or not. So let's go ahead and graph it. Well, actually, right before we graph it, let's do the absolute value one first. So the mean absolute error is going to be mean absolute error 143. Interesting. Interesting that this number is bigger than this one. What does that tell us? Well, first thing is there's probably no issue with outliers. In fact, I'd say that the data set has no outliers that are problematic, because otherwise the RMSE would be higher. So yeah, that's pretty much all I can say so far. So yeah, but let's plot it, because again, that's when we really kind of get to see whether this is good or bad. Also, we can do the one more that was on the example, and that one I'm just going to put in here, and you can look at it later, is the R2 score. Whoa. That does not feel right. Oh. Ooh, okay. I see an issue with both of these. This should have been Y, not X. Again, we're comparing what the correct answer is, what we expect. When I copied and pasted it, I put Y. So let's look at those errors again. There we go. This looks more better now. So now our error between the RMSE and the MAE is smaller than the RMSE. So now I take back the point about outliers, because the outliers could be problematic. But also now this looks more right. It's very weird to get this number being higher than the RMSE. So that should have been a red flag. But what really was a red flag was the R2 score, because the R2 score should be between 0 and 1. 1 being that your model is like top notch, 0 being that your model is bad. And if you ever get a negative R2 score, then you're like, your model is just really, really bad. Like, you don't want that. If something, Google it. People will be like shocked and stuff. But it's possible to get a negative one. It's really bad. But yeah, no. So when I saw that number that was like 10,000 something for that to score, I was like, whoa, something is really wrong. 0.47. And model is so-so. Like, I would say it could definitely have room for improvement, because we want to see something close to 1. 0.9, I would say, is like an ideal spot. If you get 1, that's also a red flag of overfitting. 0.9 is where I would be happy, like a happy place for me. This is pretty low in the sense that I would want to use something better than linear regression for this. But that's okay, because again, we can do this diabetes data set with something else, and with like neural networks, and see if we do any better, which we will. But yeah, definitely play around with this and see if you can improve this. But okay, let's go ahead and plot it, because I still want to see a plot. So Matplotlib, it's an awesome library. We definitely should check it out more sometime. But if not, you should check it out on your own time. It's very trivial to use, though. Most of the stuff is like well documented. So all I'm doing right now is I'm making a scatter plot. So I'm using the scatter function for scatter plot. And then I am passing in the x-axis, which is my testing, and my y-axis, which is my prediction. My testing, I should say. So x is what I feed it, y is what I should get back from it, and this is the correct ones for both. So this should be a bunch of dots. And let's go ahead and color these black. Let's run it. Nothing happens because I forgot to do PLT show. Also, let's just put some ticks. Actually, well, here, let's just plot it without the ticks first. See what it looks like. All right, so here's our data. So you can see on the X and Y, now the scale starts to make more sense when you look at it. When you see these RMSE of 41, 41's a small scale. It's not too bad. Like, think about the range of these numbers. It's going like this number and this number are almost like 100 apart. So having an error of about 41, it's not too bad. So I'm guessing the line is going to be somewhere like this. But let's go ahead and show that. So first let's add some text to this. Let me just rerun it again so you can see what that looks like now. That hurts. It looks prettier now already. But let's go ahead and make the line that our model predicted, so that y equals mx plus v. Make that into a line instead of a scatter. And for that, I'm going to make the test points, but then I'm going to put my predicted points. I'm going to make that a blue line and just give it some width. Okay, so again, I'm going to plot my test. So this is both plotting the test data set part. I'm taking the test, and instead of giving it what I should expect, I'm giving it what I'm predicting. So that's a predicting, so I can compare them both, basically. So as you can see, the line is kind of where you would hope it would be, right? Because I mean, this is kind of looking like a trend that it's going like this. You can see it hits one point almost on the spot, but not quite. So again, if you were just thinking of accuracy as like how many points I'm hitting, this would be at like 0%. That doesn't make it necessarily bad because it's predicting it decently well. 50-50, I'd say. And you can see that this is probably what's really hurting our root mean square error, like these points here, that point there, that point here, and that point there. But in general, you know, the data is very like noisy and like thick per se. So there's no real good way of graphing this. Maybe if you did like a polynomial where it like curved like this, I'm thinking. Maybe like this. Yeah, so something like that maybe. But you risk overfitting. Because like I could totally overfit this to go like this. Well, does that really generalize well? I don't know if the data, because I mean that seems to make it like it's going to go really noisy, like really like all over the place here. And it might just be really straight here. So I have to find a middle ground for that. But yes, I think a little bit of a sign would help here a little, per se. But yeah, it's a little better. It's a lot better to see that. It's a lot better to see it visually now. We can see that at least the model is trying its best. Here's me running it again just to see what we get. Okay, so this is again, the blue line represents our prediction. That's our model that we made. The dots, the black dots represent the test data, which we know what the answer to is. We know that's what we expected. So that means that like at 0 here, we should be getting a 50. At 0.08, we should be getting about 200. But our model says we should be getting about, well, actually, they're both over 200. This is more like 220, and our model is saying like 218. So the error there is about 2. Root mean square error is taking all of these numbers, the square of all of these numbers, and then averaging and then taking the square root of that. Mean absolute error is just taking the difference between the line and the dots, adding all those absolute value of all of those, adding them all together, getting the average. So now that we can see the numbers 41 and 50, we can see that for most of these, that's about right. So like, if we look at this is about 105, and you can see that like this is at 150. So that's about 105 to 150, that's about 45, which kind of goes around there. This one's also about off by 50. This one's off by over 100, basically. Well, this is 50 here, so maybe like 75. So this one's the one that's kind of messing with us. This one here is like 225, and this is over 300, so another 75. So you can see why the error is what it is now. Like, these numbers make sense based on this image. But yeah, to summarize, what I did is I imported my libraries, scikit-learn, Matplotlib, NumPy. For scikit-learn, I imported some of the metrics, but also the dataset and the model that I'm going to use. I went ahead and loaded the dataset into two variables, x and y. I then extracted only one feature because I only wanted to test this with one feature because there's more than one feature in this case. I then went ahead and did my split between training and test because I need test data to be able to evaluate whether my training worked well or not. I just go ahead and slice it. I have to slice both the x and the y's because they have to match too. I gotta make sure I don't underline them, otherwise things don't work. I then start my model. I train the model by feeding it the training data set, so the x train and y train. After the model is trained, I want to see if it's good trained or not. So I go ahead and test predict by feeding it the test part of the data set and comparing it, and then getting that prediction from it. Now I'm going to compare it with what I know is right by running it to the error computations, like mean absolute error, R2, and mean square error. And you can see that all of them feeding it what I expect the right value is versus what my model gave me, which is prediction. I can see as a result that it's not by any means a very good model, but it's not bad per se. Visually, you could see that it's kind of in the right. It's got its heart in the right place, and that's it. That's what we have. So if I wanted to feed it a brand new piece of point, what I would do is I would call the predict function and feed it that point, and then see what I get back from it and compare it to what I expect if I know. And if I don't, because it's like brand new, it's just like I'm already deploying this. Like I'm like, oh well, it's the best I could do. I'm deploying this to the real world. We've called predict on it. It gives you something back. You sure as hope that's one of the good ones. So that's all I have for you today. Like I said, in the next video, I'm going to go ahead and actually show you an example of my own with data set of my own that not my own, but I found it online. I had no clue what I was going to get from it, so I ran it. It all seems to work. I don't like the graph at the end, but I think that's a data set that we can use. So hopefully this was all very straightforward and you followed along so that we can kind of take it to the next level on the next video and do our own examples. And ultimately what I want you to do is to do examples of your own with your own data sets, and if it's something that would benefit you. So I'll see you then on the next video. But until then, take care and thanks for watching. Have a good day.